Okay, today we're going to look at Chapter 6, Functions, and the section is 6.1, Introduction to Functions. So functions, what is a function? Well, when one input of a relation is linked to only one output of the relation, it is called a function. In other words, there's only one y for one x. You can't have multiple. Now, function notation is represented as f of x, and the way it's written is just f parenthesis x. And this f of x is actually equal to y. So normally we might have, y equals mx plus b. Well, now we're going to say it's f of x equals mx plus b, and that's going to be the function. So f is a function of x is what it means, and f of x is read f of x. So I'll be reading this as f of x, or if it's a different variables, whatever it is. You can have, different function letters, and you can have different variable letters here. So it could be of anything. It could, be p of t. So p of t is how that would be. Now, sometimes we get a graph and we can test to see if the graph is actually a function. And the way to do that is called a vertical line test. Now, basically what you do is you have your graph drawn out, and then you draw vertical lines through the graph. And if it only intersects a graph once, everywhere you try, then it would be a function. But if it intersects more than once, then it's not a function. So for example, if we had the following here, something like we had a straight line y equals x, no matter how many vertical lines we draw, it only crosses that line once. But say we had some kind of a weird sideways parabola, no matter where we draw, except for right there on the vertex, everywhere we draw, it's going to hit it 2 times. And so that's not a function. So that's not, and that is, okay? And so what we're going to do now is we're going to test a whole bunch of these different graphs and see which ones are function and which ones are not. And I guess this was pretty obvious when I just made this one up, so I didn't even know this would be one of them. But we looked at that one before, and that y equals x, that one is, because of the vertical line test, it only crosses it once. Now a circle, no matter where we cross it, pretty much you're going to hit it there, so that one is not a function. Now a parabola facing down, again, no matter where we cross that, it's only going to hit that line once, if you draw a straight line, of course. But yeah, so that one is going to be a function. Now this wavy line, no matter where you cross it, again, it's going to only cross one time. And so that one also is going to be a function. Now this one, this is a vertical line. So if you draw that vertical line right on top of it, that one is not going to be a function. Now this is half of the parabola I showed last time. So no matter how many times you cross that, that one is going to be a function. Now if we had drawn the second half down below, then it wouldn't be a function, but looking at only the top part, it is. Now this one, first time we do it, nope, it's not a function. Now again, this one, no matter how many times we do it, it looks like it's only going to cross once, so that will be a function. So that's how we can use a vertical line test to determine if it's a function or not. And what it means is, if you notice, if we had one x, then we ended up with 2 y's, and that's not allowed. Here, every one x, we just got 1 y out, and so that's why that one is a function. So whenever we didn't have a function, we had 1 x and we got 2 y's. Now we have things called the dependent variable and the independent variable. It might be easier to think about the independent variable first. That's the x. When we have a equation y equals mx plus b, that's going to be our input. We're going to put that into the equation, and we're already going to know our m, and we're going to know our b. And when we plug in our value of x, whatever one we plug in, then we're going to get some y out. And so x is the independent variable, which is also called the input. And this output, y, now remember, that's also called f of x, and so that's going to be our dependent variable. So it depends on what we plug in for x. So if we plugged in 1 here, that's going to give us one value of y. If we plugged in 2, that's going to give us a different value of y. So it's dependent on what we plug in for x, and so this is going to be our output. So f of x or y is going to be our output value. So What are the independent and dependent variables? Well, we're really only looking at the whole thing as a whole. So if we're looking for independent, you know, and dependent, we really only have to look at that piece right there, because we know that this value here, that n in this case instead of x, that's going to be the independent. So n is equal to independent. And what is the dependent variable? Well, that's the whole g of n. And so that's going to be the dependent, okay? Now, what about this one? Well, here, t, that's what we're going to have to plug in every time, so that's independent. And then h of t, that's going to be our dependent variable, okay? Now we're back to f of x. In two cases, it has two different things, but in each case, x, so for both of these, x is going to be equal to the independent, and f of x is going to be equal to the dependent. Okay, so they both have the same labels, but they have totally different values for what the function is equal to. But the overall dependent variable is f of x, and the x is going to be our independent variable, which is going to be our input. Now, what if we have something like a word problem here? So it says a cost in dollars C of x, where x is the number of miles driven of rented car for a day, is C of x equals 1.25x plus 33. And it asks again, what is the dependent and independent variable? Well, what's dependent? Well, dependent is the C of x. So that whole thing is a dependent. And then our x is our independent variable, because no matter what we plug in here, that's going to be our input. And then our output is going to be the whole C of x. And so similarly, this one, the profit in dollars P for a certain commodity N, where N is in units, is given by the function P of N equals 25N squared plus 375N plus 850. And so here, that is going to be our whole thing. It's going to be our dependent variable, and our N is going to be our independent variable, because that's what we're going to plug in for the input, and our output is dependent on what our input is, and that's our P of N. Okay, and so really, again, this, we could have written this as y equals 25n squared plus 375n plus 850. So again, it's P of N or y, so it kind of depends on how you want to look at it. And y, we know is the dependent variable, and in this case it's n instead of x, but the n is going to be our independent variable. All right, so some things here, kind of what values can we actually plug in for our x's, and then what values come out for y. That's kind of what we're looking at here. And so the domain of a function is a set of all inputs of the relation. So what is legally able to input into the relation. And so these are all the values of x that we can have. Now the range is a set of all outputs of the relation. So all values of y can be. Okay, so whatever we can have. And a lot of times these are easier to find if we draw a graph. Not always, we'll always find it if we draw a graph, but sometimes we can find it without having to draw the graph. Now, when finding the domain, what we do is we find the values to exclude. That's the best method. So these may include values that will make the denominator 0, or give you a negative under the square root, or a combination of the two maybe. And then we have fractions. When we have those, what we do is we set the denominator equal to 0 and solve for the variable. And so that's kind of what we're talking about here. Where would the denominator be 0? Well, we set that whole denominator equal to 0, solve for the variable, and the values that we obtain are the values that cannot be part of the domain, and they have to be excluded. Now, when we have radicals, what we have to do is we have to set the radicand part, which is that part under the radical. So, if we have, x squared plus, 11, we set this part here, the radicand part, less than 0. So we would set x squared plus 11 less than 0, and then we'd solve for the variable. And then any values that we obtain should be excluded from the domain, okay? And so that's what we're going to do. And so we're going to have a couple examples here, and we're going to specify the domain initially only. And so if we look at this, what values can we plug in here? Are there anything we cannot plug in for x? Well, really, this is just an equation of line. So no matter where we plug a value in, we can plug it in from negative infinity all the way out to positive infinity, and it will be legal. So the domain is going to be, now it kind of varies. You know, sometimes they'll say to put it into um, interval notation. Sometimes they'll say to do things. So you have to kind of watch what they say. But I'm going to say in this case, we're going to put it in interval notation. And so that's all real numbers, basically. So we could also say all real numbers. So we're going from negative infinity to positive infinity. Okay, because no matter what we put in here, it's going to work. Now, what about here? Now, this one, remember, when we had the thing, it said set the denominator equal to 0 and solve for t. Okay, well, if we do that, t squared equals -1. Well, that's not possible. When you square something, it's always going to be positive. So basically, there's no t we can exclude here, because if you think about it, if we put a negative here, it's going to always be positive, and we add more positive. So again, this one is going to be nice. It's going to be all real numbers we can use. Now, if we'd said, okay, well, this is a -1, then we start having things where we can actually find for values we can't use. And that's what we come up to with the next one. But in this one, again, it's just going to be all real numbers. So no matter what we plug in for t, it's going to become positive. +1 is positive, so there's no values ever are going to reach us to get us 0 here. But in this one, we could hit a 0. And so what we do is we set that x squared minus 25 equal to 0. We add 25. And so x squared is equal to 25. Now what we're going to do is we're going to take plus or minus the square root of that. So we're going to take the square of that, and it's going to be plus or minus the square root of that. And so x equals plus or minus 5. Those are the values we have to exclude. And so when we do that, sometimes it might be easier to kind of look on a number line. Sometimes it just kind of varies from person to person. But those two are the values we cannot have. And so we can have everything, you know, all the way up to that point, but not including it. And then we can have from that point all the way to the next point, and then we can have all the way past that. And so what we do to get this interval notation, we kind of write it as we look at the number line. Well, it's going to go from -infinity up to -5, but not including that -5 because we have to exclude it. Union, because we want everything. Now we're going to go from -5 to +5 because we go all the way up to here, but we can't include it, so we have another parenthesis. And then we have union again, and now everything above that. And so we have 5 all the way up to the positive infinity. So these 2 points are points where we have to exclude them. And the way we exclude them is we say, you know, parenthesis, parenthesis, and those can't be there, and parenthesis, parenthesis, it can't be there, but everything else can be there. And so that's how we're going to write this one when we can't have 5 or -5 for x value. All right, what about the next one? Well, this x squared minus 3x minus 4. Well, this one again, you know, it's going to be some kind of a parabola. And so basically any value for x we plug in here is going to work. If we plug in -200 and square that, there's nothing wrong here. There's no denominators, so it's okay. And there's no radicals, so it's okay. And so here, again, we're going to go from -infinity up to positive infinity. Anything we plug in here will work. Now the next one, we have a radical as well as a denominator. Well, we already saw that one, we said that x could not equal a -5 or a 5. So if we go ahead and start plotting this on a number line, so we 5, -5, it can't equal that, it can't equal that because we already looked at that over here, and so we've done that one. Now what about the numerator? So the numerator, what it said to do was take what's under the radical, so the 3x minus 12, set it less than or equal to 0, and solve for x. So we'll add 12. So 3x is less than 12, divide by 3. So x is less than 4. And what this means is anything less than 4 we can't have. And so if we look on our thing over here, so here's 4. So we can't have anything from basically this position that way. We can't have any of that. Okay, so what does that mean? Well, that means we can only have, maybe we should put what we can have now, maybe in red, we can have from this position forward, we can have, but this way we can't have. So when we do that, what does that say? Well, okay, now when we go this way forward, we have to remember we still have this point we cannot have. So we're going to go from 4 to 5 union 5 to infinity. Okay. And so we've left out everything to the left because of this here piece. We've left out the -5 and 5, and so when we have this part, we have to take out that 5, and so that would then be our domain for this one. So this is going to be our domain. Now, if we put, we should probably say our domain is equal to that, and D is how we represent domain, and if we were doing range, we would represent the range with an R. Okay. Now we can also evaluate functions, and that's just going to be like, if we had an equation and we started plugging in values into the equation, we can do that because, remember a function, say f of x equals 2x plus 2, well, that's the same thing as saying y equals 2x plus 2 because the y is equal to that f of x. And so now all we're going to do is we're going to plug in values for 2 and solve for y, or in this case, we're going to solve for f of whatever the x value we plugged in. And so there's several ways we can write this in function notation. So we can say, well, okay, we have f of x, and then we're going to say plug in x equals 3. So that means we're going to plug 3 in place of x for everything in the function represented by f of x. Okay. Now, if we have p of 2, what that means is we're going to plug in 2 because that's going to be our independent variable. And we'll plug that into that whole whatever function it is and solve, and that's going to give us what p of 2 is. Okay. Now, similarly here, we have f of 3b. We're going to plug in 3b into whatever, in this case it's f of x, and so we're going to plug in 3b for every x in our function and then solve, and that's going to give us what the f of 3b is equal to. And on the last one here, what it says is we're going to take k of t plus 3. So we're going to take t plus 3 and plug that in for every x in the k of x, the original function, and simplify, and then find out what the whole k of t plus 3 is equal to. Okay, and so that's what we're going to do now. All right, so for each function, we're supposed to evaluate at the value or expression and what is the ordered pair. So basically, this is going to be, what our x value is, and then we're going to come out and we're going to solve it, and then we're going to get out some y value. All right, so we're going to find f of 0. So we're going to plug in f of 0. So f of 0, and what that is equal to is 3 times 0 plus 1, and that's equal to the absolute value of 1. Oh, and then we have plus 1 here, sorry, plus 1, plus 1. Well, absolute value of 1 is 1, plus 1 is 2. So our ordered pair is x is equal to 0, y is equal to 2, and so that's going to be our ordered pair, 0, 2, because our 0 was our x. We solved after we plugged it in, and we got our y is equal to 2. All right, so here, well, we know x is minus 2. So we've got that down already. So now we just plug that in. So f of minus 2 is equal to 3 to the negative 2 minus 2. And so now we just kind of simplify from there. Well, what's 3 to the negative 2? Well, if we change that to a positive, we can say that's 1 over 3 squared. Remember, we just changed the negative. We flip it over the sign or the bar. And so if it was in the denominator, it goes to the top. If it's in the numerator, it goes to the bottom. Minus 2. Well, 3 squared is 9, so that's 1 over 9 minus 2. Well, here we have to get a common denominator, so that's going to be 9 over 9 we have to multiply by. So that's going to be 1 over 9 minus 18 over 9. So that's going to be minus 17 over 9. And so that's a minus 17 over 9. And that's our ordered pair plugging in negative 2 into our value here. All right, let's do a couple more. Here we have k of 3. So what we want to do is we want to plug in 3 into the n. So k of 3 equals 3 minus 1. And so that's equal to the absolute value of 3 minus 1 is 2. Absolute value of 2 is 2. Okay, and so that's our value. And so our ordered pair is what? Well, it's going to be 3 comma 2, because that was our y, that's our x, and so we have our solution. Now here we have x is a negative 9. So we can go ahead and write negative 9 here because that's our x. And we're just going to find what that is equal to. And so we have a negative 9 squared plus 4. Well, what's negative 9 squared? Well, squaring it is going to give us 81 plus 4. That's going to give us 85. And so then our answer then for our ordered pair is negative 9 comma 85, because our x plugged in here, when we square it, gives us 81 plus our 4 gives us 85. All right, a couple more here. What we have here is a negative 2 we're plugging in, and it looks like I dropped off where our function is, so it looks like it was p of t equals. So we want p of negative 2 equals, now we have a negative 2 times 4 to the 2 times negative 2 plus 1, and then we have plus 1 here, and so that was a times. And so now what we have to do is simplify in parentheses. So we have a negative 2 times 4 to the, well, that's going to be a negative 4 plus 1 is negative 3, and then plus 1. And so that's going to be a negative 2. Now we're going to take that to the other side, and that's going to be 4 to the third plus 1. All right. Well, 4 to the third, we have to figure out what that is. And so 4 times 4 is 16 times 4 is going to give us 64. And so that's going to give us a negative 2 over 64 plus 1. Well, we can reduce that to 1 over 32. So that's a negative 1 over 32 plus 1. Well, we have to get a common denominator, which is 32 over 32. So that's going to be 32 minus 1, which is going to be 31 over 32. And that should be our final value. And so we have negative 2 comma 31 over 32. Okay. All right, so the next one, we have to plug in a whole expression. We have to plug that in for what x actually is. And so what we have to do is say, well, h of minus 1 plus x equals 3 times 1 minus 1 plus x, and then still plus 2. So now we have to get rid of parentheses. So that means distribute. So that's going to be a negative 3 plus 3x plus 2. And so that's going to give us a minus 3 plus 2. So it's going to be a minus 1 plus 3x. And so that's as far as we can go. So our ordered pair is minus 1 plus x. And our output is a minus 1 plus 3x. Okay. And so then that would be our actual final value here as far as the ordered pair. All right, 2 more here. What we're going to do is we're going to take h of n plus 2. So that means we're going to take the whole n plus 2 and plug it in here. So that's n plus 2. And so that's going to be 4 times n plus 2, and then still plus 2. Now we have to get rid of parentheses, so that means we're going to distribute. So that's going to be 4n plus 8 plus 2. So that's 4n plus 10. And so that is going to be our output from that input. So that's going to be n plus 2 comma 4n plus 10. And that's going to be our ordered pair. So then it really depends on what your n is what you get out for your actual value for your ordered pair. So if n was, 1, you'd have 1 plus 2 is 3. And then if 1 here, it'd be 4 plus 10 is 14. So it'd be 314. All right, here we have a more complicated, and we have to have a fraction we're going to add in. So h of x over 4 equals x over 4, the quantity squared, plus 1. Well, when we square that, we have to square the numerator and the denominator. So that's x squared over 4 squared is 16 plus 1. Well, now we need to get a common denominator. So that's going to multiply by 16 over 16. And so we'll have x squared plus 16 all over 16. And so this is going to be our x. This is going to be our y. And so we have x squared plus 16 over 16. So 1. And so then that would be our final ordered pair. And again, now it's going to depend on what your x is, depends on what your actually output here would be for your ordered pair. So if we had 1 again, that'd be 1/4, and this would be 17 over 16. So that would be how it would work out. And so that's all I have for this section.